Hi everyone and very good day to all of you. My name is Muhammad Dini Iskandar. We are Group 4 from Section 2 Group 1. Today we're going to present Part B of our assignment for the MID 2433 Instrumentation and Control. Our project is titled Improvement for Plastic Bottle Filling System Using Ultrasonic Level Sensing. The team consists of 4 people, which is Badri, Harid, Syed Ahmad Fitri and me, Daniel. Moving on to our system overview, our case study focused on automated production line. Right now, the system is fully automated and runs on a sequence controlled by a PLC or programmable logic controller. Here is how it works. A conveyor belt driven by a DC motor moves the bottles along the line. Proximity sensor detects exactly where the bottle is, so the system knows when to stop. A solenoid valve then controls the liquid flow, and a pneumatic piston mounts the cap before a DC motor tightens it. It sounds efficient, but in reality, this setup has some major limitation, especially when it comes to accuracy and handling different bottle size. So what's the real issue here? The core problem is that the current system operates as an open-loop control system. Essentially, the filling process is blind. The PLC is programmed to fill the bottle based only on a preset time. Because there's no feedback from the actual liquid level inside the bottle, any small change can ruin the batch. If the flow rate or pump pressure changes, or even if the liquid viscosity varies, you will get inconsistent filling. This is gonna lead to overfilling, underfilling, and a lot of unnecessary product wastage and spillage. Currently, the only way to fix this is through manual adjustment, which is really slow down the efficiency. That's exactly why we are proposing the use of electronic level sensing to give the system the eyes it needs to be precise.
For the proposed solution, we improve the existing plastic bottle filling and capping system by upgrading the instrumentation device used in the process. The main sensors introduced are an ultrasonic level sensor, a load cell sensor, and a photoelectric sensor, all integrated with a PLC control system. These sensors work together to ensure accurate bottle detection, precise filling volume, and consistent capping performance. Compared to the existing system, the proposed solution reduces manual intervention, minimize filling errors, and increase overall production efficiency. First, the photoelectric sensor is used to detect the presence of a bottle on the conveyor. When a bottle interrupts the light beam between the transmitter and receiver, the sensor sends a signal to the PLC. This signal allows the PLC to stop the conveyor and activate the filling process only when a bottle is correctly positioned. This prevents spillage and ensures accurate bottle alignment before filling. Next, the ultrasonic level sensor measures the liquid level inside the bottle without direct contact. The sensor emits ultrasonic wave toward the liquid surface and measures the time taken for the echo to return. Using this time delay, the distance between the sensor and the liquid surface can be calculated. The distance is calculated using the formula where V is the speed of sound in air and T is this time taken for the signal to return. Once the required liquid level is reached, the PLC closes the solenoid valve to stop filling. In addition, a load cell sensor is used to ensure precise filling based on weight measurement. As liquid enters the bottle, the load cell experiences mechanical deformation. This deformation changes the resistance of the strain gauge, producing an electrical signal proportional to the applied weight. The output signal of the load cell is directly proportional to the applied force, where force is calculated using force equal mass multiplied by gravitational acceleration. By setting a target mass value in the PLC, the filling process stops automatically once the desired weight is reached.
To understand how this hardware integrates into the workflow, let's look at the system schematic. Our process is structured as a closed-loop control system. First, detection stage. A proximity sensor identifies the container, and the PLC manages the conveyor motor via relay switching to ensure precise positioning. Second, feedback and signal conditioning. As the liquid enters, the ultrasonic sensor continuously measures the level. This data is fed back through the PLC input module. The third one, control logic. The PLC acts as a brain, comparing the real-time sensor data against the user-defined set point. The last one is output action. Based on this comparison, The PLC controls the solenoid valve to achieve an accurate fill. Once complete, the container is moved to the final output stage, where a pneumatic piston and DC motor perform the capping. This loop ensures every container is filled and sealed with maximum precision and efficiency. Moving into hardware selection, we conducted a rigorous evaluation to justify our choice of an ultrasonic sensor over a traditional mechanical float. We focus on three key performance indicators. First, hygiene. Traditional float require direct contact with the product, which possess a significant contamination risk. By using an ultrasonic sensor, we achieve a non-contact operation. The sensor stays above the liquid at all times, ensuring we remain in full compliance with food safety standards. Second, reliability. Mechanical systems are susceptible to wear, jamming, and hardware failure. Because the ultrasonic sensor is entirely electronic with no moving parts, we significantly minimize maintenance needs and prevent unexpected production downtime. Finally, flexibility. If we need to change bottle size with the float, we could have a manually reposition the hardware. Our system allows for high adaptability. We can modify field level settings directly through the PLC programming, enabling rapid changeovers without halting operation. This selection ensures the system is not only cleaner, but significantly more durable and versatile.
Okay, next I will explain the advantage and limitation of our automatic filling system. One main of the advantage is the use of a non-contact ultrasonic sensor. Since the sensor does not touch the liquid, it helps prevent contamination and keep good hygiene. It's very important for industry like food, beverage, and pharmaceutical. Another advantage is high filling accuracy. The system monitors the level liquid in real time during filling. This means the system can automatically control the filling process based on the target level. As a result, overfilling and underfilling can be reduced. This helps to save material, increase efficiency, and ensure every bottle has a consistent fill level. The system also improves automation and reliability. It reduces the need for manual checking and make the process safer in industrial environments. However, the system also has some limitation. Firstly, the ultrasonic sensor may not work well when there is formed strong liquid, movement, or vapor. The condition can cause inaccurate reading. Secondly, the initial cost is higher than traditional system because it uses sensor, PLC, and automation equipment. Thirdly, the system needs proper calibration and correct sensor position. If not done correctly, accuracy will decrease. Lastly, skilled workers are needed for PLC programming, maintenance, and troubleshooting. In high-speed operation, extra signal filtering may be needed for stable reading. Okay, now I will move to explain the maintenance and calibration plan for the system. Regular maintenance is important to keep the system working properly. The ultrasonic sensor should be cleaned often to remove dust, water, and dirt. The solenoid valve and pump must be checked for leak or blockage. This part directly affects how well the system fills the bottle. The conveyor belt and motor should also be inspected to ensure smooth movement. Misalignment can cause error in bottle position. The pneumatic piston and DC motor should be checked for smooth operation. All electrical wiring and PLC connection must be inspected to avoid faults. For calibration, the ultrasonic sensor is first tested using a non-distant. This ensures the sensor gives accurate reading. Then the correct bottle height and target liquid level are set in the PLC. Test filling is done and the actual level is compared with the target. The system settings are adjusted if needed. Calibration should be repeated regularly or after any change to the system. In general, basic cleaning is done daily, system check weekly, and full calibration monthly. These maintenance plans help keep the system accurate, reliable, efficient, and safer for long-term use. That's all from me.